Hey, Calc students, this is Mr. Beck. Today we're going to be discussing three sections out of our book. The very first section we're going to discuss is all about continuity. So to highlight a little bit of the reasons why we talk about continuity, let's go back to some of the problems that we did in the homework last night, where we established what is the limit as x approaches a number from the left. And as we're approaching this number 1 from the left, we're going to be talking about whenever x is less than 1. Then the second thing we're going to do is find the limit as x approaches our c value. In this case, our c value is 1 from the right, which means we're going to be looking at these two, or those series of equations. And last but not least, once we know that both of those are identical to each other, then we're going to say, what is the overall limit? So going into our problems, the limit from the left, we get is 0. The limit from the right, we get is 3. And you can see that just by plugging it in. And it's this first case that the limit is not going to exist, and the reason why it doesn't exist is because these two numbers are not the same. This is our formal reason of saying the limit from the left is not equal to the limit from the right. There are three overall reasons why the limit doesn't exist, if you remember from last time's notes. Those three reasons I have highlighted over here. The first is oscillation. Oscillation is going to be one of the weirder behaviors. It happens, but we don't discuss that nearly as much. The second case, which is what we just highlighted, is the limit from the left is not equal to the limit from the right. And then the third is unbounded behavior. So as you approach C, it's unbounded, it goes to infinity. So unbounded behavior. Now, because the limit from the left and the right are the same on both of these problems, let me just go ahead and fill those in. Because these are the same, we could say the overall limit is the same as well. So, what this highlights is continuity. So in order for us to have a continuous function, which if you remember from pre-calculus, continuity is an extension of domain. So if we have the domain, then we can say where are we continuous on the domain. But this definition of continuity is threefold, and the AP loves discussing this definition of continuity. So please, please, please make sure you know how to define continuity. And we define it in the three ways. The first way kind of makes sense that in order for you to have a continuous function, f of c has to be defined. So number one thing, f of c is defined. So let's state that f of c is defined by just listing it as a point. The second statement that we need is going to be that the limit as x approaches c of f of x exists. So in order for us to have continuity, we need to have the point defined, and then the limit has to exist. Now, as you can see in this graph right here, if point number 1 is correct, that we have a definition, or that point defined, and then the second one is the limit exists. If you notice, that is not a continuous function. There's a hole in this graph. So in order for us to truly have that continuity, we need to say the limit does equal the value of the function. So this forces this one point to get moved down into that spot. So when the limit equals the value of the function, then we know we have continuity. So all three things need to be stated. So how does this relate to discontinuities? Obviously, if we have a continuous function, life's happy. If we have a discontinuous function, let's describe those discontinuities. And if you haven't noticed in calculus, we're looking at all the different functions. We're looking at different aspects of functions. We want to be able to describe it and describe it accurately. And this is a big change from what you probably saw in pre-calculus or earlier, where pre-calculus says, hey, can you do all these things? Let's be creative with it. But with calculus, we're starting to turn to a more formal, do you understand why things work? And that's really what the AP tests in the end. You understand the theories behind calculus. So understanding continuity by definition is going to be huge. And then understanding by definition, what are the discontinuities and how do we describe them? So if the limit exists, which I believe I highlighted that in purple, so let me go back to the purple. So if the limit exists, but the point doesn't exist, which is what we showed in the graph to the left, that's what we call removable discontinuity. So visually, you can see this removable discontinuity just because it's a displaced point or just a hole. Now, the reason why we call it a removable discontinuity comes from, if you remember the functions that we had, f of x equals, say, x plus 1, x minus 2, over x minus 2. We know that that created a hole in the graph, but we were able to find the limit. And let's kind of like apply that idea of what calculus is um, the way we found the limit was we used the theorem that stated if we create a function which is equivalent to the function that we want, in essence, if I create that function which is equivalent to the function that I want, except at a certain point, we can evaluate the limit by plugging it in. So that theorem says we could do this, but we just removed the discontinuity so that we could find the limit. Let me go ahead and put it back and just stress it one more time. It's called a removable discontinuity because in order for us to find the limit, we removed what made it discontinuous. The other type of discontinuity is the non-removable. Those non-removable have the two different cases of unbounded behavior. So the non-removable discontinuity is unbounded behavior, which is vertical asymptotes. This is just one of those examples. Or we have a jump, and the jump is if you have a solid point, actually, we just have a break in the graph. And when I say a break in the graph, it's a displaced y value break. The limit from the left is not equal to the limit from the right. So going back to example 1a, this is a jump discontinuity. Then what we did was we looked at example number 3 and we just put this to practice. Could we determine what the discontinuities are and then describe them? And just like I said, the non-removable discontinuities emphasized here. This is our unbounded behavior, and then this is our jump. And that's why those are non-removable. Then we have the removable case. Let's go ahead and go back to yellow. We have the removable case, and that removable case occurred right here. Notice that the limit exists. That's going to be your key feature. If the limit exists, it's removable. So over here, does the limit exist? Yes, that limit is 3, in case you're wondering. So that limit, which I'm going to call L, is 3. Because the limit exists, but it's discontinuous, it's removable. And then once again, we have a jump discontinuity. And that jump discontinuity, I believe I used purple on the other one. This jump discontinuity means the limit from the left is not equal to the limit from the right. Now you heard me say this over and over and over again, and the reason why I'm saying it so many times over and over and over again has to do with the fact that I want you to be able to look and understand by definition what we're doing. So it's not just trying to come up with the answers. The answers definitely are important, but it's that thought process to get to the answers. Now, problem number 4, I asked for what is the continuity of example 3b? And what I would like to do is I would like to highlight some key distinction. That if you look at 3b, the domain of 3b is from 0 to 5. But the continuity shows that there is some form of break, even though that the domain exists everywhere from 0 to 5. And so by looking at domain, definitely domain helps us understand what functions are doing. But then if we take it to that next level and say, we have our domain, what is the continuity on that domain? And it allows us to be able to get good information from the function without actually having to see the graph. So knowing that we have discontinuities tells us quite a bit. Or tells us or gives us more information. I probably should say it that way. So when it comes to the definition of continuity, to have continuity on the open interval, the limit has to exist everywhere, or really. Oops. Let's go into the highlighted and go back to yellow. So this is basically saying we're continuous for every C. Now, for a function to be continuous on a closed interval, we do once again have that continuity on the open interval. However, this is where we use one-sided limits to say we need to make sure the limit at the start of the interval, the right-handed limit equals the value of the function, and then left-handed limit equals the value of the function on the endpoint. So for us to have continuity in the closed interval, meaning why did we have these brackets? We had those brackets because we wanted to make sure that we're establishing the endpoints existed right with the function anyway. One of those small details, but kind of nice for us to go through. I do have 3 graphs here. With the 3 graphs, one of the purposes of me giving these three graphs on your note sheet is because I want to just re-emphasize, do you remember how to graph all the different things, especially piecewise functions, put it all together. Wanted to highlight for example 5a, do you guys remember how to draw quick graphs of parabolas? We have the pattern, we drop down 1, then we drop down 3, then we drop down 5, because it models the perfect squares. The change from 1 to 4 to 9 to 16 is, I guess from 0 to 1 to 4 to 9 to 16 is 1 plus 3 plus 5 plus 7 plus 9. So do you remember how to draw quick graphs? Remember how to put together piecewise functions? So these are kind of like review problems. Then we say state the intervals of continuity. We do have continuity from negative infinity to 2. You'll see in my notes a lot that I will put a closed dot and an open dot together if I have two piecewise functions coming together. That's mainly for me to highlight that this is occurring, because otherwise you would just see a dot and you wouldn't know what's happening. For part B, I do like this style of problem because it asks you to be able to draw a graph. It's a little bit more complex, but this graph has both a vertical asymptote and a hole. That vertical asymptote does occur, and this is the non-removable continuity, does occur when we are not able to remove the factor in the fraction. Then we have our removable continuity, which is this x plus 1 over x plus 1. If we remove it, then we come up with the function 2 over x minus 3. And I still like to keep that domain x does not equal -1. But that indicates that we have a hole here. So we are able to find the location of the hole. The location of the hole is at -1, 1/2, because we find the limit by plugging -1 into this function. And then C, just an interesting case where do you understand how to use piecewise functions with absolute values, and it just brings back a little bit of tangent notation or tangent graphing. So again, these problems are designed to use the interval of continuity while rehashing some of the old skills that we're not always familiar with. That's okay. So one of the things that I would like to point out is how I was able to graph this. If you remember, working with absolute value inequalities, this tells us that x is going to be greater than or equal to 1. And because it's a greater, it's a disjunction. Or we would say negative x is greater than or equal to 1, so x is less than or equal to -1. So putting it all together, that's how I come up with this half of the graph and this half of the graph. All right, I said the definition of continuity was the first major definition that the AP likes to test based off of what we're doing. The intermediate value theorem is the first big theorem that gets tested over and over and over again. So the intermediate value theorem, one of the ways that I describe it has to do with this morning, the temperature was 53 degrees as I was coming into school. I know that the temperature is supposed to be about 75 today in the afternoon. So my question for you is are we guaranteed that we're going to go through the temperature of 70 degrees? If we start off at 53 and we end up at 75, are we going to have to hit the temperature of 70 degrees? And the answer is obviously yes. And that's because temperature is a continuous function. So in order for us to be guaranteed any intermediate value, intermediate value theorem, we first must have continuity on the closed interval. And then second, we also have to say that the value we're looking for has to be between f of a and f of b, meaning the value that we care about has to be between the top and the bottom. So if the value we care about is, in this case I said 70, 70 is between 53 and 75 degrees. If you look at this graph right here, this graph shows that the intermediate value does not have to occur if there's a discontinuity, which is why continuity is pretty essential. So anytime I have you do problems, what I have you do is I have you list out, we must have continuity. So I'll be checking to see if you can show that we have continuity. Now, the proper way of saying that is, yes, we have continuity from 0 to 1 because quadratic functions or polynomial functions are continuous everywhere along the domain, and the domain is all real numbers. What I care about is I want you to show me that you've checked for continuity. The second condition for the intermediate value theorem is that we have to find f of a and f of b to show that that 0, which is what we want, is in between f of a and f of b. You guys use the intermediate value theorem in pre-calculus doing this kind of mentality. So what I showed in class was, suppose f of x equals, I'm just going to write it as 3x minus 1 and x plus 2. I know what the zeros are. I don't really care about the zeros right now. And as I'm emphasizing what I'm trying to do. So suppose, let me multiply it out, 3x squared plus 5x minus 2. Suppose I did not know the zeros and I was trying to determine where the zeros are occurring. One of the things that I teach my pre-calc kids is let's find f of 0, which is -2. Let's find f of 1. F of 1 is 6. So because we jump from a negative to a positive, we know that there is a 0 in between. And then the benefit of knowing this is then we can use the P over Q, the rational zeros theorem, to figure out what those are. And so it would be what are the factors of 2 or factors of 3, et cetera, et cetera. For what we're doing in calculus, we still might do that approach, and it still might be important, but we tend to use the intermediate value theorem to guarantee that we're going to have all these different values. And again, the ideas that we have in calculus is not just about, hey, let's do this problem, let's do this problem. Can you understand why we know something's going to occur? Because many times we're not going to be able to find what that value is. However, we know that one exists there. Example number 7. Oops, let me change back to the highlighter. If you notice, I mentioned that we have continuity. I did find the f of A and f of B. I showed that this k value that we're looking for, let me go ahead and highlight those in a different color. K value that we're looking for is in between f of A and f of B, so the intermediate value theorem applies. Yay. And then this problem says find it. So if you notice, I found it, and then I showed there are no additional solutions other than 2. Where over here, I didn't actually find what f of c was, and that's because I was not asked. Or I did not find the c values because I was not asked to. So those are the major ideas behind continuity that we care about for the AP. So we move on to section 1.5. 1.5 is about infinite limits. Now, students tend to get confused a little bit between infinite limits and limits of infinity. For infinite limits, that is when the limit as x approaches c from either the right or the left equals infinity or negative infinity. Versus limits at infinity, that keyword at says what is the limit at infinity, or as x approaches infinity, which is more proper. So the infinite limits are when the limit does equal infinity. Keep in mind, infinity is not a value, it's more of a description. So because that is a description, the limit does not exist. So limit does not exist. That infinity is really a descriptor of how it does not exist. So infinity describes how it doesn't exist. All right, so let's first talk about these infinite limits. And the infinite limit is where the limit fails to exist because the numerical value approaches positive or negative infinity. So if you notice, we do write this, and it's really our algebraic way of describing what happens graphically. And I'm all about the Triforce, where I try to encourage you to think about all 3 components: what happens numerically, what happens algebraically, what happens graphically. Connecting those key ideas is essential for me. Then vertical asymptotes, our official way of saying what a vertical asymptote is if we have a rational function, so let's call my rational function, and f of x or f of c does not equal 0, and then in the denominator, g of c does equal 0, then we have a vertical asymptote. Basically, if we have some number over 0, that indicates we're going to have a vertical asymptote. So where does that exist algebraically? First example I have, if you notice, the x minus 3 is a removable discontinuity. So then if we said, what is the limit as x approaches -3 of f of x? We put that in, we get -1 over 0. I realize -1 over 0 is very, very bad notation. I do want to show that, or I do want to mention that I might show a little bit of the bad notation, but please know that I don't like the bad notation. This is really just kind of the mental work to say what is happening. I know that if I divide by 0, one of 2 things is going to occur. We have a whole or we have an asymptote. Because this is a number over 0, that's going to indicate that we have an asymptote. and therefore x equals 3, or x equals -3, excuse me, is going to be the vertical asymptote. So this is our vertical asymptote. For part B, a lot of people like to immediately say, oh, x equals 0 is a vertical asymptote because we have that x in the denominator. But that would be very bad thinking, because we have to look at it as tangent of x over x. And if you remember from our last time's notes, we can break tangent of x into sine of x over x. So that way, if we found and established the limit, what is the limit as x approaches 0 of f of x? It's going to be 1 times 1 over the cosine of 0, which is 1. By the way, that limit is 1. So at x equals 0, it's not a vertical asymptote. So the only vertical asymptotes are really going to occur when cosine of x equals 0. So vertical asymptotes are when cosine of x equals 0, and that would be at x equals pi over 2 plus pi n or k. I prefer to use n because n usually indicates that we're going to be increasing by integer values. So some properties and limits. Let's discuss the properties and limits first. That infinity plus or minus a number is still infinity. Infinity times a number is either going to be infinity if that number is positive, or that number is negative infinity if that number is negative. Now, what I'm trying to highlight here is that to determine whether we have positive or negative infinity, we can treat infinity as a value. And like in my mind, if I had $1 trillion in my bank account, that's just a lot of money. That's really my infinite value for, or at least my idea behind infinite value. So if we have infinity, we can treat it as a number, even though it's not entirely a number. So like all of this notation, it's not exactly the most proper notation, but this is designed to help build very quick and efficient thought. One of the things I do want to point out is L is not allowed to equal 0. If L equals 0, there are a lot of different things that are going to happen, and we'll discuss that more next time, actually. Infinity divided by a number, same kind of properties. And then we have an additional lemma where if we take a number and divide it by infinity, we do get 0. Now, this is some personal notation that I made up, which is a dangerous thing in mathematics to make up notation. But this kind of models the limit as x approaches 0 from the right or the left. By having our limit be 0 with a plus or a negative, it tells me, and what it indicates to me is, are we approaching that x-axis from the bottom, or are we approaching that x-axis from the top? So this is my way of connecting like a more numerical approach to what's going to happen with the graph. So in the first example, if I plug in 0, I will get 0 minus 1 over 0. So this 1 over 0, and I'm going to kind of do this over here. This 1 over 0, yeah, let's not do it that way. So this 1 over 0, because it's a negative 0, negative zeros I realize don't exist, but 0 minus negative infinity is what our result's going to be. Therefore, 0 minus negative infinity is infinity. And what you should realize is that sign rules work if you treat infinity as a really large number instead of just an abstract concept. For part B, 8 divided by, in essence, infinity is going to be 0. We know it's not actually 0. So once again, very, very bad notation, but I was just trying to get across the meanings behind what's going on. And keep in mind, I don't like messing up the notation or having improper notation. For part C, we could treat secant, look at the graph of secant as x approaches pi over 2 from the right side, sorry, from the left side, then it should go to infinity. One way that students also like to see this, because they don't always remember the secant graph, 4 divided by cosine of x. So if we take a look at the graph of what does cosine of x do, as x approaches pi over 2, then cosine of x approaches 0 from the positive side. So this is really saying 4 over 0 from the positive side, which is how we get to a positive infinity. And last but not least, for this example, you take the limit as x approaches -3 from the right side. So if this is our asymptote of x equals -3, And what I'm doing is I'm just looking at like the natural log of x plus 3 graph. Then our denominator is negative infinity, our numerator is -1. So if we have a negative divided by a negative, we do get a positive value. So what this means is we're approaching 0 from the positive side. AKA, if I wanted to take a look at the graph of this, then as x approaches -3, y will approach 0 from the positive side. So it'll approach 0 from the positive side. For problem number 3, use a table of values to find that limit. I just plugged that into Desmos and I started getting bigger and bigger and bigger numbers. And those bigger numbers indicate that we're going to go to infinity. Pretty straightforward. If you'll notice, I'm not a huge fan of plugging in all those decimal values. I know many of my students aren't either. But the reason why we do it is just as an indication, or is just to really kind of help identify what's going on. This last section is our limits at infinity, meaning what happens when x approaches positive or negative infinity. And one of the reasons why limits are the most powerful function in mathematics, in my opinion, is because you could use limits to determine what happens on a small region, what happens on a large region. Limits break order of operations where you can apply limits at different points. So our job right now is to use the given functions to find the limits at infinity or negative infinity. Now, what I'm trying to tie here in my notes is these limits at infinity do relate to horizontal asymptotes. Because when x approaches infinity and the y value approaches a distinct number, which we see kind of for the definition of horizontal asymptotes, if the y value approaches a distinct number, then we're going to have a horizontal asymptote over there. We're going to learn that we can have multiple horizontal asymptotes. A good example of this is the inverse tangent graph, where the inverse tangent graph looks like so, where we do have y equals pi over 2 as a horizontal asymptote, and y equals negative pi over 2 as a horizontal asymptote. So it is possible to have multiple, or really 2 horizontal asymptotes. But the definition of that horizontal asymptotes is what happens at infinity or negative infinity. In pre-calculus, we knew that horizontal asymptotes occur based off of the degree in the numerator and the denominator. I'm not going to rehash that because I know a lot of you remember that already. But what I would like to indicate is, like, if I plug in, say, 10 million to all of these x's, if I plug in 10 million, the numerator is going to end up being a smaller value than the denominator. What we can do is we can take this x value out, and I take the greatest common x out of both numerator and denominator. Those do reduce out properly because x is not going to be 0. We care about what's happening in x is infinity or negative infinity. And so in the end, after we factor out, we get an expression that if we plug in infinity or negative infinity, we will get 6 over infinity. And 6 over infinity tends to go to 0. And when x goes to positive infinity, the same thing is going to occur where you have 6 over infinity, which is going to tend to 0. These degrees are the same, and if you remember from pre-calculus, if the degrees are the same, then y equals 3/4 ends up being your horizontal asymptote. And so what we're doing is finding the limits at infinity. Once again, I took out the largest degree that I can take out of both of these, which in this case is x squared. These will reduce out because remember, x is an actual number, not just, or x is an actual large number, not just 0. And so then we get an expression that I can substitute infinity in. So 1 over infinity squared, roughly 0, which is how I get all of this. And I think at this point, you probably can figure out that's what's going on in part C too. With part C, if I take out the x squared over x squared, reduce those out, I am left with an x in the numerator. And because I'm left with an x in the numerator, that's why this is negative infinity, because we end up with negative infinity plus 0 over 1 minus 0, which is just negative infinity. This one is infinity plus 0 over 1 minus 0, so just infinity as well. One of the big limits at infinity that most students don't really pay attention to is e to the x. If you remember, the graph of e to the x looks similar to this. So as x goes to negative infinity, the y value goes to 0. So we have a horizontal asymptote of y equals 0. Or if we're looking at the graph of e to the negative x, it'll look similar to this. So we have the horizontal asymptotes here, y equals 0. So in example 5, our goal is to find all horizontal asymptotes. On problems like this, I typically don't make students write down all their answers because they can think through it in a fairly efficient way. I showed all the different algebraic approaches to how I got there. If there's any questions, just let me know, but most students seem to be able to do these problems on their own. But when it comes to example number 6, this is an absolute value in the numerator, and with any absolute value, if you haven't noticed, I started off these notes with the absolute value problem, or with a piecewise function. It had like 2 or 3 parts, but the absolute value function forces us to have to break this into its 3 different components. And we don't always have to put this middle component right here, that at 0 at x equals 0. But the reason why I like to do it is because then it allows me to say, what is the limit from the left? What is the limit from the right? I think I had those backwards. So limit from the right, limit from the left. And then this middle piece gives us the function value. And so we do have continuity, and it kind of really rehashes that we have continuity if the limit from the left equals the limit from the right, which equals the value of the function. In this case, we're talking about infinite limits, though, that if we used kind of like the rational idea behind what we did in pre-calculus, that at infinity, we have the y value of 2/3. At negative infinity, we have the y value of negative 2/3. So therefore, we have 2 distinct asymptotes. The first asymptote is y equals 2/3. The second asymptote is y equals negative 2/3. So our graph, we're going to have a positive horizontal asymptote there. We'll have a negative horizontal asymptote there. And then the reason why I keep bringing up these absolute values as a piecewise function is because we will see it a couple times as the square root of x squared, which is the absolute value of x. So in example B, that's where I used it the most, that this limit as x approaches infinity of the square root of x squared, we can turn the square root of x squared into a just x versus, now let me do this in a different color for you. Let me do this in green. If this problem had said the limit as x approaches negative infinity, then we would have turned this into a negative x over x times the square root of 1 plus 1 over x over negative 3 plus 1 over x. Now, as far as the algebra goes, most students tend to follow the algebra, except I do want to highlight one thing. I do want to factor out, and this is kind of the way that I look at it, what is the, what can I take out of both the numerator and denominator? Like how many x's can I take out and reduce it that way? Which is why I looked at it here. In part B, x is the degree of the numerator is 1, the degree of the denominator is 1, so it made more sense to take out an x over x. But the x that we had to take out was kind of distinct as the square root of x squared. C, pretty straightforward. If I look at E is infinity minus infinity, and infinity minus infinity is indeterminate. So what I did was I combined those natural logs together, and once again, limits are such a powerful thing that we made the limit go from the outside of the natural log to the inside of the natural log, and that allows us to establish what the overall limit is. On F is a little bit of, I don't even know a good way of saying it. F is kind of a creative approach to finding limits based off of what we've done. If we do a substitution of the limit, that substitution I kind of indicated here, if x is 1 over t, as x goes to infinity, 1 over x goes to 0. So in case you're kind of confused, t is 1 over x. If we do some algebra, t is 1 over x. So as x goes to infinity, 1 over x goes to 0, meaning t goes to 0. So I can rewrite that expression, the expression that I have with the limit as t approaches 0, 1 over t times the tangent of t. And then once again, we see the sine of t over t. which is something that we've explored multiple times. G, if you look at G just by itself, you end up with infinity minus infinity, and infinity minus infinity is indeterminate. So the approach that I took on this problem is I multiplied by the conjugate. So don't forget, multiplying by the conjugate is a very, very powerful approach. And then just simplify the algebra. And once more, you see, let me highlight this in the greenish color. We end up with the square root of x squared. What I did was I factored out the square root of x squared. So that x came from the square root of x squared. And why is it just x and not negative x? That's because we're approaching positive infinity. And then the rest is the algebra. In H, once again, multiply by the conjugate, shows you just how powerful the tool we have. When it comes to I, J, and K, I, J, and K, what we end up with is 1 plus 0, but that's not really a true 0 to the infinity power. So this is 1 plus a really, really small positive number to the infinity power. We cannot do this algebraically yet unless we have L'Hopital's rule. L'Hopital's rule is something we're going to cover next semester, maybe at the end of this semester if we get to it. But we have to do this numerically, and we can put this into a Desmos or calculator to solve. Really, all three of those we can do that for. That shows that you can always do some algebra to simplify it. And the reason why we can't use L'Hopital's rule is because L'Hopital's rule is proved using derivatives, and we haven't even gotten to that yet. So we have to use the table of values in order to come up with our overall answer. So hopefully you understood everything that I talked about in the notes, and they are benefiting you. So have an amazing day.